you guys keep asking phenomenal questions, and you keep pushing me beyond stuff that I know, and then I go learn a lot and only just barely sort of get it. Our goal today is just for you to have a general sense for what happens when you apply the Hamiltonian operator to a Slater determinant wave function. And remember that the Slater determinant is how we have to express our wave function so that it can obey the Pauli principle. So for a simple 2-electron wave function, you can imagine this being like hydrogen or H2 or perhaps helium. We've got electron 1 and electron 2. We've got spatial wave function A, and the 2 electrons can share that spatial wave function if they have opposite spins. And to get the Slater determinant, we'll multiply across and then subtract this product. And that's just formulating our wave function as the Slater determinant just prevents us from having 2 electrons with the same spatial distribution and the same spin. You okay with that so far? We showed last week how that was important. So because we don't want to write as many things, we're going to simplify this and just use I and J to mean in the top row you have electron 1 in spatial orbital A with spin alpha. We're calling that I subscript 1. If instead electron 1 is in spatial wave function A but spin beta, we'll call it J1, and then so on. And remember, we're using these subscripts 1 and 2 as sort of artificial labels for electrons, which we of course can't actually do, but doing this makes sure we keep the Pauli principle. And then if you evaluate the determinant I1 times J2 minus J1 times I2, that would be how we would write a wave function for this molecule. Okay, and of course in a molecule with many electrons this would get even more horrible and complicated, but I gotta tell you, this is all I can handle. I can't do more than 2. It just is not going to work with my brain. Okay, so we've talked before about getting expectation values out of the wave function. This comes from Schrodinger's equation, but you apply the Hamiltonian to your wave function, then multiply it by the complex conjugate of the wave function. Then you've got to divide it by basically the wave function squared. That normalizes everything and gives you your energy. So if we just take this expression here, for our Slater determinant for our wave function, and put it in every time we've got the psi symbol for wave function, we end up with something like this. And this is just that determinant as we've written it out. Okay, so you can treat operators to some extent like algebraic quantities, and this is what I was trying to show you last week, but I think I got a little bit confused. Hamiltonian applied to this first I1J2 term, multiplied by the complex conjugate of I1J2, and that gives us this term highlighted in yellow. And so we can go on expanding out Hamiltonian applied to I1J2 times minus J1I2, and that gives us the purple term. Similarly, if we take Hamiltonian applied to minus J1I1 times I1J2, we get the green term, and then similarly we get the blue term. And we can do similar things on the bottom. So that's just algebra. Don't necessarily worry about copying it down. And you'll have these notes available. But this is what our expression for energy starts to look like. Now, if we think about what each of these terms does, I went and did the math. Let's see if I can, no, did I not? Oh, right. I'm going to just copy down the Hamiltonian again. And I went and applied the Hamiltonian to I1 times J2 and then multiplied it by I1 times J2. And do I recommend going through that? Not necessarily, because I only just barely sort of got it. But the way it works out for this particular term, you basically get the kinetic energy of electron 1 in spatial orbital A with spin alpha, its attraction to the nuclei, and then Coulomb repulsion with the other electron. And at the same time, separated out in a different term, you get the kinetic energy, all calculated from this, you get added the kinetic energy and attraction to the nucleus of electron 2 in spatial orbital A with spin beta, along with Coulomb repulsion to electron 2 instead of electron 1. Or rather, to electron 1 instead of electron 2, sorry. So later on, when we show you the Hartree-Fock equation, you're going to have an H with two subscripts I. That's going to stand for kinetic energy of an electron and nuclear attraction. Okay? They call that the so-called core integral. And just like we saw in... Anyway, yeah, we call that the core integral. Yes?
The little volume thing is getting in the way.
Oh, sorry. Let's see. Thank you. Yep, thank you, Kim. I'm sorry about that. I'll scroll up a little bit. Oops. Switch to my pointer. So the HII term just means kinetic energy of the electron and attraction to the nuclei. Kinetic energy of this electron with this spatial orbital. And it also, from this term, if you look at our expression for the Hamiltonian, here's your kinetic energy, here's your attraction to the nuclei, and then here's electron-electron repulsion. And for this term where you've got I1 and J2 before the operator and I1 and J2 after the operator, you just get a straight up Coulomb repulsion term. That's electron-electron repulsion, okay? If you go to one of these weird terms where you switch the spin or you switch, let's see, where before the operator you have I1, and then after the operator you have J1. It turns out, and the same thing for J2 and I2, it turns out the kinetic energy portion of the Hamiltonian goes to 0 when you do that, because if you go back and look at how we defined I1 and J1, notice that I1 has spin alpha, J1 has spin beta. The integral of alpha times beta over all space is just 0 because spins are orthogonal. So the kinetic energy term goes away. The term for nuclear attraction goes away. And all you're left with is this strange integral where it's derived from the electron-electron repulsion, but we're switching things. So it's not really electron-electron repulsion. Notice before the integral it's I1, after the integral it's J1, before the integral it's J2, after the integral it's I2. This is the exchange or switcheroo term in the Hamiltonian, and it's really difficult to attribute any physical meaning at all to it until you start to expand it a little bit. So I went ahead and put back in our definitions for I1 and J2 and so on. I1 is electron 1 in spatial distribution A, spin alpha. J2 is electron 2 in spatial orbital A with spin beta. Notice that the spins are constant and they're not operated on by this operator, so we can factor them out and integrate them on their own. So if we take electron 1 with spin alpha and electron 1 with spin beta, that integral goes to 0. So the exchange integral, the K integral, is 0 between electrons with opposite spins. It is non-zero for electrons with parallel spins? Now, it's a fair question to ask, Josh, in this Slater determinant where we've only got 2 electrons and 2 orbitals, don't they always have to have opposite spin? And I'm telling you yes. But remember that we're going to have molecules with multiple electrons, okay? And in particular, if we have molecules with more than one unpaired electron, we're going to get a favorable exchange integral term, but only when they have parallel spins. So this is a bonus energy you get when you have 2 electrons that are unpaired and they have parallel spin. Okay? And this, it turns out, is the origin of Hund's rule that you learned in general chemistry. Do you remember learning something like, let's suppose we have a set of d orbitals in some element that are like that. Do you remember learning that you would first fill them all up with parallel spins and only then do you start pairing things up? That's the reason, okay, because of the K integral. Because you get a favorable exchange integral term when you have parallel spins. And this is a purely quantum mechanical term. You don't get this from classical mechanics, but it does explain important things about molecules. All right. So with that in mind, let's see, and then the purple term is another one of our switcheroo terms where you have J1 before the integral and I1 after the integral. This is another exchange integral. And then the blue term is actually just equal to the yellow term. So overall, if we apply the Hamiltonian to a Slater determinant, we get a sum of, just a second, I'll ask you in a second. We get a sum of kinetic energy, nuclear attraction for each individual electron, plus nuclear repulsion between that electron and every other electron in the molecule, minus the K integral when spins are parallel.
Can you say that all one more time? Sorry.
Yeah. If you apply the Hamiltonian to a Slater determinant, you get a big long list of terms that represent for each electron its kinetic energy, its attraction to the nucleus, its repulsion with every other electron in the molecule, and then an exchange term that's only non-zero when electrons have parallel spin. Which is why, and this is the thing I didn't understand when I first tried to tell you about the Hartree-Fock equation, I didn't understand how we got from this point where we were talking about the wave function as Slater determinant, and then your text shows you this expression here, and now you're talking about individual wave functions again. And I thought, where did the Slater determinant go? And the answer is, if you make the assumptions required to go through this process, you can separate out the energies for each individual electron. Okay, so this is our Hartree-Fock operator representing the Hamiltonian acting on an individual electron wave function, now with the spin portion embedded in that symbol. We've got the core integral that again represents kinetic energy plus nuclear attraction. You've got the J integral, which represents electron-electron repulsion. And then you've got the K integral, which is the exchange integral, and it's non-zero when I and J have same spin. One thing I was not able to learn, I tried. I was going to say I tried really hard. I don't know how hard I tried, but I did try to learn what the factor of 2 here is. Your text gave an explanation that was unsatisfactory. It refers to the fact that for the J term, you don't have to have parallel spins, but for the K term you do. And so there's twice as many spin combinations that work for J than work for K. I don't know why the 2 is there. I'm not going to ask you why the 2 is there. All right, Dakota, I'm sorry. You had a question, and I said I'd come back to it.
Yes, with that diagram of 5 orbitals, is
Yeah.
it possible that if the top orbital were low enough, the exchange energy might be enough to compete with the...
That's a good question. Is it possible that if this energy distance were enough, that the benefit of having parallel spins would compete with this delta E? I think so. And this gets into a whole area of chemistry that I don't really know anything about. We'll talk about when we start dealing with molecular orbitals of simple systems, what the difference is between triplet carbene and singlet carbene, and it does have to do with that K integral.
Yeah, in this case we could choose singlet, triplet, or quintet if we can order one out.
Oh, yeah. Cool. Yeah, good. Other questions? Okay, so the whole point of this is that the K integral is the explanation really for Hund's rule. But then the Hartree-Fock equations are our first sort of opportunity to now calculate, to now guess, what these wave functions are, and then apply the operator and then see what energies we get out. And we're going to use something called the variational principle, whereby we're going to iteratively make changes to these wave functions and see that our energy gets lower and lower and lower. And when we converge to the lowest energy we can get, we will hopefully have something that represents something close to reality. Okay, go ahead.
So this whole time we've been working with wave functions as more of a variable than an actual, we know what this wave function is.
Uh-huh.
Okay.
That's right. Now we're going to go ahead and say, okay, wave function for electron I. I'm going to say, if I have 5 different atoms in my molecule, I'm going to do a linear combination of atomic orbitals. If atom 1 comes with a 1s orbital and a 2s orbital and 3 2p orbitals, I'm going to have coefficients for each of those atoms. And this is what I'm writing here is non-physical. This would be like if we had 4 hydrogens in our molecule, right? And we're going to try to make something with all of those. And there's only one atomic orbital that we allow to be present for each atom. In reality, in molecules that have heavier atoms, carbon, nitrogen, oxygen, heteroatoms, we're going to actually increase the list of things that we can put in there to not only the valence orbitals, but sometimes we're going to add in d orbitals, not because the d orbitals are actually involved, but because the more options you give the wave function, the more it can approximate reality. So your text goes through and talks about something that's called a basis set, and the different kinds of computational stuff that you can do. In addition to the way that the energies are calculated, the basis set represents which alphabet of orbitals or functions are you going to put in to try to approximate what the wave function looks like. Yeah?
Are all of these 5 functions Slater determinants?
Oh, are all of them Slater determinants? No, I think they go into the individual wave function for a given electron, and then that becomes part of the Slater determinant. And remember, the Hartree-Fock equations come out of that Slater determinant. So by the time you get here, you've already taken care of that. Yeah.
So the 5 functions are just hydrogen wave functions?
Well, it would depend on our molecule, right? If it was carbon, we would include at least these, if not more. Now, I don't know all, and I didn't write down in my notes because it's in your text and it's fairly straightforward to follow, but your text takes you through a bunch of different types of basis sets. And in general, the more functions you can include, the more realistic your representation of the wave function can be. So there are a lot of methods that are based on sort of the Hartree-Fock equations. One of the challenges, though, is that Hartree-Fock or HF methods don't account for electron-electron correlation. Notice that we have basically assumed that each electron feels repulsion with every other electron, but we're not, and we're going to continue cranking on the calculation until the numbers stop changing. But in general, what we're going to observe is that energy in reality is going to be lower than the energy we calculate from Hartree-Fock. And the difference between reality and what we observe, or what we try to calculate in Hartree-Fock, we're going to call the energy of electron-electron correlation. And there are a lot of methods that try to deal with this. Electron-electron correlation is movement of electrons out of the way to minimize their repulsion. And sometimes you can get fairly reasonable answers with small molecules without taking into account this thing, electron-electron correlation. However, if you're interested in, say, anything that involves van der Waals forces, dispersion forces, induced dipoles, you're going to miss out on some of that, because induced dipoles involve movement of electrons in molecules to get away from each other temporarily. So as an example, I've been trying to learn how to do computational chemistry to evaluate energies of non-covalent interactions. And on Thursday and Friday, I'm not interested in benzene interacting with benzene for my research. It's kind of interesting from an academic point of view, and we'll come back to it. But one of the ways that benzene can interact with itself is through what's called T stacking, or edge-to-face stacking, where an electron-poor hydrogen on one benzene ring, I don't know what color we'll use for electron poor. I guess electrostatic potential maps use blue. And then you have the sort of electron-rich face of the benzene ring. Sort of looks sad, right? It sort of looks like a sad benzene ring there. And I was doing some calculations to try to optimize the geometry of this complex, how far away it should be, and then calculate the energy. And I was getting a reasonable geometry, but the energies I calculated were way off from what had been reported in the literature. Mostly this is because I don't know what in the heck I'm doing with Gaussian, and I'm self-taught. So, Michael, if you want to come by and teach me some stuff, that'd be useful. But it's likely that I'm not using the method that's appropriate. I'm either not using the appropriate basis set, or I'm using a method that doesn't account for electron-electron correlation and dispersion effects. What I was doing was density functional theory with B3LYP or something like that. That describes a particular set of functionals that are used. And depending on what corrections you apply to that, I've started to read that it is bad at dealing with dispersion effects. So, moral of the story is, you're trying to calculate things, you have to make sure that your method and your basis set are appropriate to the problem that you're trying to deal with. So at some point in the next couple weeks, I'm going to introduce you guys to Gaussian, and we're going to do a few calculations. I would like for you to get to the point where when you're doing your research and you have a question, you can just run down to the computer lab and submit a job and try to get a sense for the way things are. I have never been able to do this until this summer. I'm just barely learning to do it now, but it's already seems to be tremendously useful. All right. So I want to review briefly where we've come so far, because that basically finishes up what I want to do in chapter 14. We're leaving a lot undone, of course. But I want to review what we've identified over the past couple of weeks as the source of some of the basic rules of organic chemistry. Okay? Remember, electron delocalization is stabilizing, and that's because of the kinetic energy operator in the Hamiltonian. Spread out wave functions have lower magnitude second derivatives, smaller changes in slope, and so will therefore have lower energy. Another principle that comes from this that we didn't necessarily talk about is more nodes in an orbital. Moore's nodes? No, let's see, get rid of the S. More nodes equals higher energy in general. So if you were to compare a standing wave like this with a standing wave like this, you would instinctively say, oh, and assume they're the right length and whatever, I'm sorry, I'm hurrying. You would instinctively say, okay, this is the higher energy orbital, and it is, but the reason for that is it takes a big change in slope to cross zero, and it takes a bigger change in slope to cross zero repeatedly. So this wave function is going to have a higher kinetic energy than that one. All right. Second principle that we talked about was from the two orbital mixing problem, where we determined that the bonding orbital is stabilized by a certain amount and the anti-bonding orbital is destabilized by a higher amount. And that was due to this overlap integral that appears in the denominator for our energies. When the overlap integral equals 0, then bonding and anti-bonding orbitals are evenly spaced. But when it's not 0, then the bonding orbital isn't as stabilized as the anti-bonding orbital is destabilized. And we talked about how that's the origin of closed shell repulsion, perhaps steric hindrance, because if you take two filled orbitals, both filled with 2 electrons, and you mix them together, you're going to populate the higher energy orbital, which is always more unstable than the lower bonding type orbital is. All right? So this is important because this is behind another principle of OChem, which is nucleophiles attack electrophiles, right? Nucleophiles have electrons that they want to, well, they don't want anything. We're trying not to anthropomorphize molecules. But nucleophiles have electrons that can become more stable by sharing them with something that has an empty orbital. We don't say nucleophiles attack nucleophiles because of closed shell repulsion. We also talked about, because of this same two orbital mixing problem, I showed you how if the two orbitals are not equal in energy, the bonding orbital tends to resemble the lower energy orbital. The anti-bonding orbital tends to resemble the higher energy orbital. And another way of saying that is if the two orbitals are not equal in energy, the coefficient in your wave function is bigger on your lower energy atomic orbital than on your higher energy one. Yeah, go ahead.
So you got that from normalization?
We got this from doing the two orbital mixing problem, but dropping the assumption that these two orbitals were equal in energy. And you don't have to worry about the math. But this informs us of some really important things in organic chemistry that we already alluded to. As an example, supposing you were making a carbon-oxygen pi bond, and this is a 2p orbital from oxygen, and this is a 2p orbital from carbon. Remember a principle we'll talk about later, that more electronegative atoms have lower energy orbitals. And there's a table in chapter 1 of your text where you can see by how much. But for example, if this was a carbon-oxygen pi bond, the mixing to make a pi and a pi star, the pi orbital is going to be more on oxygen than it is on carbon. And if you did the math for formaldehyde, indeed what you would see, if you did the MO calculations, is more of the pi orbital. I don't like to use hash marks. I like to use color. Oops, not that way. Egregious wasting of class time by coloring. It's okay. All right, that's the pi orbital. Similarly, you would say, and we haven't said anything about the lone pairs. We'll get to that when we start in on chapter 1. But we would similarly say for formaldehyde that most of the pi star, or the majority of the pi star, is going to be on carbon, because it is the higher energy orbital, and that's simply what the math of mixing two orbitals gives you. So maybe you remember in sophomore organic when we were talking about carbonyls, and the LUMO is the pi star, and some of you may have asked, well, why do we attack the pi star at the carbon? And I probably fudged and said, well, because oxygen's more electronegative than carbon, and therefore after the nucleophile attacks, you want the electrons to end up on oxygen, which is probably a reasonable explanation. But a perhaps more fundamental explanation is because that's where most of the LUMO is. All right. Oh, we already did that. Pauli principle we've just talked about arises from the fact that, go ahead.
So with the carbonyl bonds, the oxygen being more electronegative has more of the HOMO, and therefore the LUMO is inverted?
Well, with a carbonyl, we've got to be careful because the LUMO, or the HOMO for the carbonyl, is not the pi bond. It is, in fact, the, you'll see in a couple of days, but lone pairs that are delocalized to some extent. But yes, on the oxygen. For a similar reason, because when you do the mixing, oxygen's lower in energy than carbon. And so, yeah, the filled orbitals, yeah. So I think that's a fine way to think about it, and it's certainly borne out by the math that more of the bonding orbital ends up on the more electronegative atom.
Because we learned that the antibonding orbitals were opposite.
Yeah. So that's a decent way to remember it. And then lastly, we've explained the origin of the fact that a single spatial orbital can't have two electrons with the same spin, because if it did that, the wave function would go to 0. And then we've just talked about Hund's rule. So that's what we're going to do in chapter 14. I understand there's a little bit of anxiety about what you're expected to know in chapter 14 versus what you don't need to worry about. So if you want to ask some questions to relieve anxiety, feel free to do that. Yeah.
So,
Or for any other purpose. It doesn't have to be anxiety-based. But go ahead.
for me, the biggest potential anxiety is the math involved.
Uh-huh.
How much and what of the math would you like us to?
Okay. That's a good question. I would really like it if you could get to the point where you can figure that out as a result from the two orbital mixing problem. And I think your study guide has you go through that math. It's frankly a lot of algebra and it's a pain. It's good to have gone through it once though and convince yourself that it's true. It would be similarly good to try to calculate for the two orbital mixing problem what the coefficients are. Do I expect you to do this? No. That's just because I wanted to demonstrate quantitatively the principles that we have just described. Am I going to have you evaluate large Slater determinants and try to carry them through? I don't think so.
It's not comforting.
Okay. It would be pointless and silly for me to ask you to evaluate a 3x3 or higher determinant by hand, because you're not going to do that. If you ever needed to, you would just ask a computer to do it. And frankly, when using Gaussian, you don't do math really at all. You draw the molecule, you provide instructions for what you want the computer to do, and that's where I know enough only to be dangerous, because I'm not sure what all the instructions mean yet. Then you push go and the computer cranks away and spits out an answer, and then you need to interpret it. So doing the math by hand isn't necessarily going to be the big thing. I would like you to be able to have an understanding of what the K and the J terms mean in the Hartree-Fock equations, because that's the basis for sort of understanding why parallel spins are good in some cases. I don't know. Is there other math that you're worried about? Okay. I think the math got most bad when I was showing you all of this, and that was just mostly me trying to figure out the origin of that principle. Okay, what else? Yeah, Kim.
I feel like there is a section in the chapter that I read that maybe we don't need to worry about, but maybe we do it, like talk about all these different ways to do stuff. That's about it. What I got out of it. Does anyone else know what I'm talking about? I read it like a week ago, and so I actually don't even remember what it said.
Okay.
I just know that we didn't really go over it in lecture.
Was it like computational methods?
Probably.
Okay. Yeah, I didn't see a lot of good in repeating to you what the text said without being able to add substantial insight. You should read it and have it as a place you can go back to whenever you need to do a calculation. You're like, what the heck does 6-311G plus mean? And it's straightforward if you go back there and look at it. You can also Google it. What else? You really don't want to stop me from going on to the next chapter? I mean, come on, folks. This is your big chance.
So basically, we only need to study the problems, because all the math that you mentioned is the problems.
Yeah. What I mean, if you can do the problems, I think you'll be very well prepared. I haven't yet decided in what form I want your exam to take. It will be. I had an experience last semester when we all went remote, where I've been writing multiple choice exams for sophomore organic for years, because I hate grading, and when I ask other people to grade, they do so inconsistently, and then I have lots of regrades to deal with. And doing it by multiple choice is so much easier, because if I make a mistake, it's a trivial computer thing to just give everybody points back instead of just the people that come and complain. In any case, I gave on my not the final exam, but the last midterm, I gave it remotely, and people were taking it at home, and I didn't necessarily like how that went. You guys I'm not worried about, but there was some of these kids were like copying whole exam pages up to some website and asking for help. Please help. And getting answers back. In any case, I want your exam to be meaningful, and as I have been thinking about it, one of the questions that came up from that process is, if your exam is such that somebody could answer the questions without knowing anything simply by Googling something, are you really testing important things? Because Googling something is a useful skill, but I'm trying to get deeper understanding. So I've considered ways that I might do that for your exam, and I haven't decided yet, so I don't have a lot of details. Nevertheless, if you can do what's in the problem set, you should be fine. My other goal for you who are either grad students or might go on to grad school is for you to develop good organic thinking on your feet skills. I can't tell you how many times I've sat in a thesis defense here for graduating students, and some professor, usually Dr. Andrus or Dr. Castle, sometimes me, but I don't know that much about synthetic chemistry, so whatever. They'll ask something, and it'll be a simple issue of pKa or electron pushing or resonance, and a student will totally flub it. Okay? I don't want that to happen to you. We ought to be better than that. And so I'm considering some kind of thinking on your feet component to the exam. Like maybe you have to come to my office and draw something on the board or something like that. In any case, I'm sorry, that's neither here nor there, but that's sort of where my mind's going. Yeah?
With the math, we're not going to need to know how to do the variational theorem or Hartree-Fock calculations of real numbers?
No. Interestingly, this is the cool thing. Like, if you look it up, oh shoot, I'm trying to find the Hartree-Fock stuff. They actually did it originally by hand. Like, there's a picture somewhere of this dude with a slide rule. And in general, I don't know that many people use Hartree-Fock anymore because of its inability to handle electron-electron correlation.
Yeah, we did some runs of it in the computer lab, but even if it's not the only thing used, it's usually at least the base.
Yeah.
More complex.
Yeah, it can become a quick. If it's a fairly, it can be fairly quick.
But yeah, in PChem on the exams we had to do at least a few mild variation theorems.
So I think the variational theorem that you would be what I was talking about for the two orbital problem. That is essentially the minimizing the coefficients with respect to the energy.
Would there be a Slater determinant?
No, I don't think so. It's hard to imagine how that might be. So are there daggers looking over at Dakota's? He's giving me good ideas for the test. Yeah. Go ahead, Kim.
So I think one of the things that's concerning for me is I see you derive things, I see the conclusions that you draw, and I'm like, oh yeah, that makes sense. Are you expecting us to draw other conclusions from these kinds of things? Like, I'm imagining some kind of crazy application question that's like, think of all your organic chemistry knowledge and
Well,
see what else this applies to.
Where was I going? Back to my notes here. I can see myself asking you, why is electron delocalization stabilizing? And can you explain that in a way that makes sense? Mostly that makes sense to you. Because if it doesn't make sense to you, it's sure not going to make sense to me. Or I might ask you, given mixing between two orbitals, where do you expect most of the LUMO to be, or something like that? Yeah. Another classic example of this principle is like the carbon chloride sigma bond. Chloride, you can demonstrate the chloride orbitals, even though they're from an extra row of the periodic table, because of chlorine's electronegativity, are lower in energy than most of the carbon valence orbitals. So if you're just thinking in terms of simple make a bond, 2 electrons between 2 atoms, lower energy, higher energy, you'd say most of the LUMO should be on what? Carbon or chloride? Carbon, because it's higher in energy, right? And that is in fact a physical result. We know that because in SN2 reactions, the nucleophile attacks carbon and not chloride. Yeah, go ahead.
Does that continue to apply even for bromine and iodine with their bigger atoms?
Bromine and iodine, I think we'll talk about when we get to substitution chemistry, but in general, it has to do with their size. They're so much bigger, they can't get in as close. The bond lengths are longer and therefore weaker.
Because even if a 3p orbital is lower than 2p in this case.
Well, it turns out bromo and iodo are not that much more electronegative than carbon. In fact, iodo might be a little less. So electronegativity ceases to be a good explanation for those ones. And again, we've been probing all of this stuff at a deeper level than I've ever learned it. So yay, I will get to learn stuff along with you guys. Okay, what else? Okay, well, maybe a brief preview of Chapter 1. I'm still working on Chapter 1. I got 23 pages of notes so far. We won't do all of it. In your reading of Chapter 1, I want you to read the first section and make sure you understand these concepts in detail. They are fairly straightforward, and I don't want to spend any time on them because I think you'll be bored. But hybridization, sigma pi bonds, resonance, electronegativity, dipoles, polarizability, bond length, size, sterics. We will start to talk a little bit about the differences between valence bond theory and molecular orbital theory. And the approach that most organic chemists use is something of a hybrid. That is, we think about bonds as being 2 electrons between 2 atoms, but we also account for the fact that there are antibonding orbitals. So to just give you a preview of valence bond theory, this is popularized by these guys, including Linus Pauling, who had his hands in everything. I think he also predicted the first alpha helix, like based on knowledge of structure. In any case, we're going to think about a bond as being 2 electrons shared between 2 atoms, and so it sort of fits very well with our Lewis structure representation of molecules. The binding energy arises from the fact that those 2 electrons are shared. The 2 electrons are localized between the bond, and because of that, the orbitals that you use to make bonds on each of the individual atoms have to be localized and directed in the right orientation. If you need something to be tetrahedral, you've got to have atomic orbitals that are oriented in the directions for tetrahedral. So the way we do this, and Pauling's big insight was orbital hybridization. It turns out that as long as something is a solution to the wave function, you can mix them and match them in various linear combinations and it all still works. So, for example, we've got, if you want tetrahedral geometry, you mix 3 p orbitals with 1 s orbital, sp2 geometry, trigonal planar, sp1 geometry, linear. The thing that was sort of new to me is that you can have hybridization that has a non-integral number above the p. You don't have to mix them together in ratios that can be summarized with 1 to 1, 1 to 2, 1 to 3, and so on. And so next time we'll talk a little bit about how if you set a bond angle, if you have a particular bond angle like 107, you plug that number into there and you'll get what's called a hybridization index, which is the little subscript on the P, and that tells you how much of the P's you have to mix together and how much versus how much of the S to get that bond angle. Yeah?
If you're doing it the way they always taught us before, then if you have an sp4 hybrid like you see right there, that 4th p orbital has to come from a 3p, right? Because
No, it's actually, so that's a great question, and when you go to non-integral values, it no longer refers to how many orbitals you're mixing together, it refers to the relative ratio. So sp4 simply means 1 part S, 4 parts P.
So you might not be using the full S orbitals.
Right. So for example, if you look here for water, it's the 2 oxygen-hydrogen bonds are 1 part S, 4 parts P, whereas the 2 lone pairs are 70% P and 30% S.
So
You
more-
still only have an alphabet of 1S and 3P to deal with, but you can mix them together in non-integral ratios.
So more of the S character goes to the lone pairs.
More of the S character goes to the lone pairs. That makes sense because you've probably learned that S orbitals are more electronegative because they're lower in energy. It makes sense for the unshared electrons to be as low in energy as they can be. Okay. So we'll talk more about this next time, but until then, farewell.
Is the reading guide for chapter 1 posted already?
Sorry, is the reading guide for chapter 1 posted already? That's a big no. But I will post that later today along with my notes such as I have them, but I'm still adding on, so we'll go from there.